Hello students. In this lecture, let us solve some of the forced convection problems on flow taking place over the flat plate and that too in turbulent region. Here, the air at a temperature of 60 degrees, this T infinity is 60 degrees, is flowing over a flat plate at 125 meters per second, U infinity 125 meters per second. The plate is at 100 degrees centigrade. So wall temperature is 100 degrees and length is 1.5 meters long. We need to find out the thickness of the hydrodynamic boundary layer at the end of the plate. So delta L, which is HL or HX, both are the same, and we use X value if it is between 0 to L, that means between the leading edge and the trailing edge of the plate. We use X, or if we use at the to find out the data at any point, at a point at length L, we take it as delta L. So take it as delta L is equal to, that is at the end of the plate, the boundary layer thickness is given by delta L. This we need to find out. Then local skin friction coefficient at the end of the plate, friction factor CFL at the end of the plate, average skin friction factor CFL bar, the drag force FD, the local convective heat transfer coefficient HL, that means heat transfer coefficient at the end of the plate, then average heat transfer coefficient HL bar, heat transfer from the plate to the air per meter width. So width taking as 1 meter, we need to find the value of Q. Here we assume Reynolds number as 5 into 10 power of 5. First thing we need to know to get the bulk temperature and its properties from the data handbook at the bulk temperature. So it is obtained as 1 kg per meter cube density, then nu kinematic viscosity, Prandtl number, PR, Cp is specific heat, and the conductivity. So first thing we need to find out at the end of the plate whether the flow is laminar or turbulent. So for that, considering the critical Reynolds number, not the critical Reynolds number, we'll find the Reynolds number at the end of the plate. That will be equal to U infinity into LC by nu. U infinity is 125 multiplied by the length of the plate, 1.5 divided by nu. That will be equal to 8.89 into 10 power of 6. That is, the Reynolds number at the end of the plate is more than the critical Reynolds number, that is 5 into 10 power of 5. Hence, once we found out that at the end of the plate the flow is turbulent, next we need to find out the length of the plate up to which the flow is laminar. So for that we use the critical Reynolds number 5 into 10 power of 5. That will be equal to U infinity into X by nu. So X is equal to critical Reynolds number into nu divided by U infinity. So 5 into 10 power of 5 multiply by nu divided by velocity 125. So we get the X value as 0.084 meters. So this X is far below the length of the plate. Since the length of the plate is 1.5 meters, so compared to 1.5 meters, the laminar region length is very small. Hence, we are neglecting it and we are approximating that the flow is turbulent from the inlet itself. So by considering the flow as turbulent from the inlet, and we'll use the formula in the turbulent region from the data handbook. So already in my previous lecture, I've explained how to use the data handbook for external flow over the external flows. So please refer to that video before watching this lecture. So now consider the boundary layer thickness at the end of the plate, and it will be equal to 0.381 L divided by RE per 0.2. So L 1.5 meters, RE is 8.89 10 power 6 per 0.2. So we obtain this as the boundary layer thickness at the plate end. Then find the CFX value. CFX is the friction factor at the end of the plate, and you have two values. One is for the range of 5 to 10 power 5 to 10 power 7, and other one from 10 power 7 to 10 power 9 range of Reynolds number. Since our Reynolds number in this problem, it is in the range of 10 power 5 to 10 power 7, we use this expression CFX is equal to 0.0592 into RE power minus 0.2. Substitute, you get the value for friction factor. Then we have to find out the friction factor or the average friction factor for the entire length. So there is no average friction factor only in the turbulent region. So we need to find both in the laminar and the turbulent region. So you have to obtain the expression for both laminar turbulent combined in the data handbook, and that expression is supposed to be 0.074 REL per minus 0.2 minus 1742 into RE per minus 1. Substitute REL 8.89 10 power 6, then minus 1742, and this we obtain this value. So once we get the average CFL, then go to the shear stress. Tau is equal to FD by A, and FD is the drag force, which is equal to tau into A, and substitute tau is tau as CFL into half rho infinity square is same as in the laminar region. It is the multiply by the area. So substitute CFL half, density is 1, then rho is the velocity 125, multiply by the area of the plate 1.5 meter length and 1 meter width. So we obtain the drag force. Once you get the drag force, go to the next Nusselt number. Nusselt number is equal to HL into LC by K. HL is the heat transfer coefficient at the end of the plate. So HL is equal to NUL into K divided by LC, that is characteristic length. It is 1.5 meters. So Nusselt number is given as 0.0296 RE per 0.8 into PR per 0.33 for the turbulent region. So substitute those values, get the value of heat transfer coefficient at the end of the plate. Next, to find the average heat transfer coefficient. In the laminar region, we used to just multiply by 2. But here, we need to get the average Nusselt number expression from the data handbook. Is given as 0.037 into RE per 0.8 into PR per 0.33. Then we obtain HL as HL bar, that's average heat transfer coefficient, is equal to NUL into K by LC. LC is the characteristic length. Substitute, get the average heat transfer coefficient, and then find the rate of heat transfer Q is nothing but HL bar into AS into, that is surface area, into TW minus T infinity, and I'm again expressing this, that HL bar is the average heat transfer coefficient. We get the value as 14.4 kilowatts. Go to the next problem. So water at 10 degrees centigrade flows over a flat plate at 90 degrees. So T infinity 90 degree and wall temperature 10 degrees, wall temperature 90 degrees. And here we need to know it is water. So length and width 1 meter by 1 meter, velocity 2 meters per second. So properties of the water at bulk temperature. So 10 plus 90 by 2, 100 by 2. 50 by degree centigrade. So please make sure you are using the property table of water, not the air here. Then find the properties, then find the length of the plate over which the flow is laminar, that is XL, and the rate of heat transfer from the entire plate. So first part, we have to find the length of the plate in the laminar region. For that, you need to consider the critical Reynolds number. So critical Reynolds number is equal to U infinity into X in the laminar region divided by nu. So length of the plate till where the flow is laminar is 0.139 meters. Then to find the rate of heat transfer from the entire plate. For the entire plate means you have to consider the average Nusselt number for the entire plate and expression, that is for constant wall temperature. Then use PR is equal to per 0.33 into 0.037 REL per 0.8 minus 871. Obtain this expression, get the Reynolds number at the end of the plate. It is in the turbulent region, right? So then get the average Nusselt number. Substitute for the PR Reynolds number and get the average Nusselt number. From there, get the average heat transfer coefficient. In the previous laminar region, just multiply by 2. But here you cannot do. You have to get the average Nusselt number again expression, obtain the average heat transfer coefficient expression, and get the value. Then substitute in the heat transfer, rate of heat transfer expression as HL. This HL is nothing but HL bar into AS into TW minus T infinity. You will get the Q. Next problem, atmospheric air at 300 Kelvin. So 300 Kelvin means 27 degrees centigrade flows with a velocity of 5 meters per second along the flat plate of 1 meter length. So length is 1 meter. Plate is width of 0.5 meters. So total drag force acting, they have already given the drag force here. By Reynolds-Carbon analogy, estimate the value of heat transfer coefficient. So Reynolds carbon analogy is nothing but Stanton number into Prandtl number per 2.3 is equal to the friction factor by 2. This expression is there in the data handbook. So obtain this expression. Then before proceeding the problem, again get the properties. Since the wall temperature is not given, get the properties of the air for the air at that is for the atmospheric air itself, which is at 27 degrees centigrade. So obtain the data. Then we know that CFX, the friction factor, is equal to tau Wx by half rho infinity square. What is tau W? It is drag force by area, and that is divided by half rho infinity square. But we know the average friction factor is equal to 2 times the CFX. So get the average friction factor. So just substitute in this expression 2 into CFX, drag force 18 into 10 power of minus 3. It is given divided by area 1 into 0.5, that is length multiplied by width multiplied by half into rho is 1.177 into U infinity 5 meters square. So get the average friction factor. Then substitute in the Reynolds carbon analogy. So H bar by rho Cp U infinity is the expression for the Stanton number multiplied by PR per 2 by 3. That will be equal to average friction factor by 2. So rearrange this, get the value of H bar, that is heat transfer coefficient. Substitute for CFL bar, which is obtained in the back, rho Cp value U infinity divided by 2 into PR per 0.23. So we get the average heat transfer coefficient as 16.23 watt per meter square Kelvin. Then the next problem is air at 20 degrees centigrade flows over a flat plate of 0.8 meter long. So 280 infinity 20 degrees centigrade, length is 0.8 meters with a velocity of 45 meters per second. If the surface of the plate is maintained at 300 degrees centigrade wall surface, determine the heat transfer from the entire plate length taking air, like taking both or considering both laminar and the turbulent portions of the boundary layer. And next case, percentage error if the boundary layer is assumed to be turbulent region from the leading edge. You have two cases. So assume unit width and critical Reynolds number, and properties of the air already given for the bulk temperature. So obtain the properties which is already given. Then first case, find the Q value taking both laminar and the turbulent region. So first find the Reynolds number. It is in 10 power of 6 range. So that means it is quite high compared to the critical Reynolds number. So hence average Nusselt number value expression, use it from the combined laminar and the turbulent flow region. So that will be equal to PR per 0.33 into 0.037 into REL per 0.8 minus 871. Use this expression, Nusselt number expression. Substitute, you'll get the Nusselt number. Then average Nusselt number will be equal to HL bar into LC by K. Get the HL bar, that is average heat transfer coefficient. Once you get the average heat transfer coefficient, directly substitute in the rate of heat transfer expression and obtain the heat transfer rate. This is the actual case wherein which uses or the formulas used here considers both the laminar and the turbulent region. The next part is Q considering turbulent boundary layer from leading edge. That means we are assuming the flow to be turbulent from the beginning itself. So for that, the Nusselt number, average Nusselt number value is given as 0.037 into Re per 0.8. This expression you have to take it from the only turbulent region. So substitute. Then obtain the average Nusselt number. So average Nusselt number is equal to HL bar into LC by K. So HL bar is nothing but again L nu L bar into K by LC. Substitute. So we'll get the HL bar. That is average heat transfer coefficient. Then you get the Q value as 24,198. So this you are approximating as turbulent from the entry. So what is the percentage error? Will be Q considering laminar and turbulent minus or difference of Q turbulent divided by Q taking laminar. This is the actual or the precise value. So percentage error, so will be 24,198 obtained taking as a turbulent, since I am taking here this one first, minus considering both laminar and the turbulent region Q value which you obtained in the previous case 16,378.8 divided by the actual or the precise case 16,378. When we get the percentage error, so we obtain the percentage error to be 47% error we obtain. Thank you.